Let me begin with a word of prayer. So, dear Father, we thank you for this day. Can I thank you for this class and your creation? Just pray that you'd be glorified at what we do this day, Lord. In your name I pray, Lord Jesus. Amen. Okay, so last time we talked about potentials, and I started by saying, that the electric field we could obtain by integrating the source charge over the separation variable, the distance, separation squared times separation hat, right, as usual Griffith's notation. And I claimed that this is true, that the curl of r hat over script r squared is 0. I don't think this is entirely obvious, but once you know that's true, it's easy to see that the curl of the electric field then is necessarily 0. And since that's over an essentially arbitrary region, that gives us that the electric field is a conservative vector field, which then entitles us to write, the voltage as minus the integral of E. Now, here's the calculation. So, I just worked it out, yeah? So, like, if I look at this is my vector field, this is the jth component, is this. And then I'm like, okay, well, if I calculate, why it's just people walking on the roof. It's just the joy of this building and the stupidity of the design. But yeah, it's not just you. We're all seeing it go up and down. So I really need to rig the camera off the ceiling so it waves it the same way, and anyway.
I'll just go like this.
So the partial derivative of the separation distance with respect to xi by calculus is the difference of xi and xi prime divided by r. And so if I calculate the jth derivative, the derivative in the ith direction of the jth component, that gives me this, which gives me that. And that's pretty awesome because this, remember, is that. So if I put that down here, notice I've got j's for this, but I've got i's for that. That gives me this. I've got Kronecker delta ij over r cubed minus thrice the product of the differences of x and x prime in the jth and the ith directions. This is wonderful because this is symmetric in I and j, at which point I knew I was done. Because the curl is contracting that. You see, I can multiply this, or I can multiply that, which gives me that fj with respect to xi is the same as fi differentiated with respect to xj. You have that symmetry. So if I look at the curl, I have this, but see, I can flip it to that, and I can also, so what I'm doing here is I'm just relabeling I to j and j to I, but in the next step, I'm using the symmetry of the partial derivative piece and the anti-symmetry of the Levi-Civita symbol. But that puts me back to minus what I started with, which shows you that it's 0. This is not in Griffith's for some reason. You can guess why. It's because he's smarter than me. He knows enough not to show you that. But anyway, so then because of that, we can define the electric field to be minus the gradient, right? That makes sense because we've just showed that the curl of E is 0, so it's conservative. So we can write it as gradient of the potential, but we put the minus in for reasons I'll explain here in a bit. And we did this example last time. The thing I didn't say last time, though, was what charge distribution would give you something like this? How do you get a constant electric field? Do you guys? A plane, right? A planar charge. Where is the plane of charge here? Don't ask that question. What's that? The minus infinity z equals to minus infinity plane, you say? Yeah, fair enough. I don't know where it is. I think that question is not terribly meaningful. But I like z equals to minus infinity as an answer to my silly question. All right, so here's another example. This is the electric field of the line charge, right? S hat over S. We derive this by Gauss's law. And so here's the gradient in sphericals. Has to be equal to that, right? So how do I find the voltage, the potential? I just integrate this. Notice, of course, that V is just a function of S because apparently there's no phi or z direction dependence, right? Which is also evident from the symmetry of the problem, but we don't have to use symmetry to derive that. The calculus derives this also, right? You can go symmetry, you go calculus, either way, we get the same answer. And when we integrate both sides, we get that. So there you go, that's the voltage, the potential for a infinite line charge. You notice that this has the perhaps undesirable property of being infinity as you go to 0. As s goes to 0, natural log goes to minus infinity. And so if lambda is positive, this is going to plus infinity as we go to the axis. But it's also going to minus infinity as we go very, very far away from the axis, right? So this does not enjoy voltage 0 very far away from the distribution. But that's not surprising because this is not a finite, this distribution is an extended one, right? Like this is from an infinite line charge. So, you know, our happy-go-lucky make the voltage 0 at infinity stuff doesn't work for this example. So we're not surprised that it doesn't, you know. So just to recap, what I've done so far in these two examples is I have just done nothing more than look at E equals to minus the gradient, right? And I just integrated to find the potential. I just undid the gradient by integrating. How did we find the electric field in these examples? Well, other means I haven't even shown you, right? But Gauss's law will find the electric field. How about for the, so I decided to like try to calculate the voltage by integrating the electric field for an arbitrary point, which means I'm trying to solve these. I don't know if you've ever actually just tried to do it, but if you ever just try to actually do it, I mean, it's the basic problem. But it's the point charge at x prime, y prime, z prime. You're trying to find the potential at x, y, z. You have to solve these partial differential equations all at once, right? Now, if you rewrite that in terms of the I notation like this, you see what you're really trying to do. If you notice that this, I mean, I think we had this in the other slide. So if I take this, I can swap out like these for those. I can rewrite this as a partial derivative of the separation distance in terms of the like z, y, and x directions. And because of that, if you tilt your head and squint, you can see that what we want is partial v partial xi equals to this, which is equal to that. And once you see that, you're like, oh, so I should just put that as the voltage because I can integrate this to get this by basically like a U substitution of sorts. I don't think I would have seen this calculation if I hadn't just gone through the proof of the lemma. The proof of the lemma prepped my mind to write this calculus down, yeah? So anyway, there it is. That's the voltage for a point charge at x prime, y prime, z prime, right? And this one does have the voltage going to 0 at infinity because, of course, the charge is localized at x prime, y prime, z prime. Now, the origin is much easier, right? We know from, you know, the Coulomb field for the electric for a single point charge at the origin is this. If we set that equal to minus the gradient of the voltage, here's the gradient in spherical coordinates again. Manifestly, this has no theta or phi direction, so that means partial v partial phi and partial v partial theta. These are both 0. We're just left with a function of r alone. And then, of course, we can integrate and get our beloved Coulomb potential for a point charge at the origin, our happy place, right? This is much easier than what I just was looking at, right? When things are at the origin, everything becomes somehow much easier, right? Now, so as I say, the calculation of potential from integration of the E is equal to minus the gradient of V is a wise method to calculate the potential, especially if we can calculate E from symmetry-based Gauss law arguments. But we should review, so I did this last class, right? We went through all this. This is a rerun. So we define then, we can define the voltage as the integral from the origin for the potential. This makes sense as long as we have a finite charge distribution, right? As long as the charge is localized, we can use this as our definition, put the 0 for the potential way out there. This will make sense. But if that's not the case, you can also just make any old point the 0 for your potential, right? Probably subject to your comments about don't make the 0 where the charge is localized. That might be problematic. Like maybe I can't make, like for the infinite line charge, maybe I can't make the voltage 0 on the charge. Wouldn't be too surprising to me if that was a problem to do that. There are limits to the things we can do, but most of those annoying, sick things, they go away if we consider, a distribution of charge which doesn't extend to infinity. Okay, so this is the calculation I got stuck on last time. So annoying, so stupid. Me, not you guys, obviously. We go from infinity to here. I was writing last time dl. I had a minus here because I was like, it's because it's got to go this way. It's got to be minus. I'm an idiot. Look, r goes this way. If you're going this way, what's dr? dr is negative because it's decreasing. So this already has the minus built into it because the dr is negative since we're going from here to there. And as such, the calculation that I was trying to do last time actually works, and we can straight up calculate E dot dl as this and then integrate. Lo and behold, we're back to what I just derived. Again, Q over 4 pi epsilon naught, the Coulomb potential. All right. Now, example 6 here, we can, so I think this is yet another example of, here I'm actually wanting to work out the voltage by calculating the line integral of the electric field against the given electric field against the path from infinity. So here I'm doing the spherical shell charge, all right? So I integrate from infinity to either R1 or R2. If I'm going just to R1, what's the electric field from here to here? Outside of the sphere of charge, we know from Gauss's law, it's just the Coulomb field. It's just Q over 4 pi epsilon naught r hat over r squared. And so like for R1 greater than r, it's just the Coulomb potential, right? But for R2 less than r, we integrate from, from out here to R2. Well, okay, so that goes from out there all the way up to r, right? And then from r to R2. But what's the deal from r to R2? There's no charge in here, right? So by Gauss's law, inside that sphere of charge, spherical shell to be clear, it's a spherical shell of charge, right? This is very different from the example we have a uniform charge. And the uniform smeared charge, there is electric field inside, right? But this is not that. And so this is 0, and we just have V of R2 is equal to V of R. In other words, the voltage is constant inside there, but of course it had to be because the electric field is the gradient of the voltage, and if the gradient is 0 of a function, that function is constant. All right, so, yeah. Now, if I was to go through the same calculation for the uniformly charged sphere, it's a little bit different. Notice from Gauss's law we had before derived r hat over 4 pi epsilon naught r cubed and this, right? So if I calculate the line integral for r naught less than r, then I'm just up against the linear field inside the sphere, and that integrates to so going from infinity to r naught, I could go from infinity to r and then from r to r naught. Out here I've got the Coulomb field, inside I've got the linear field. So I get the difference of the Coulomb potential from infinity to r and the difference of the this integral from r naught to r, and that gives me this lovely formula here. All right, so there you go. Yeah, I think I clean it up in the next page. Let me go on here. So in short, when we calculate the voltage for a uniformly charged sphere, inside we get this kind of funky, Q over 8 pi epsilon naught 3 over r minus r squared over r cubed. Notice that when we let r equal to big R, this just drops back to Q over 4 pi epsilon naught 1 over r. So the voltage has to be continuous everywhere. We're going to prove that today, all right? Yeah. So there's a larger principle here, which is the superposition of potentials. If you think about this, if charge density 1 gives potential V1 and charge density 2 gives potential V2, then the sum of those potentials serves as a potential for the sum of the distributions. So and the proof is very stupid, right? So like E1 is the gradient of V1 minus, and of course the divergence of the electric field is rho 1 over epsilon naught by Gauss's law. E2 is minus the gradient of V2, and of course the divergence has to be given as such. Well, then if you take the gradient of V1 plus V2 by properties of linearity of the nabla, we have that, which is E1 plus E2, all right? So apparently the sum of the voltages, sum of the potentials serves as a potential for the sum of the fields, right? And not just that, the divergence of E1 plus E2 is given, of course, by the sum of the charge densities, which goes to show you that E1 plus E2 is in fact the electric field that is due to the sum of the densities. So it all goes together, yeah.
And is this for two overlapping fields or something?
This is for two separate charge distributions that give two separate voltages. I haven't even assumed here that these have the same zero. This calculus doesn't care if the voltage is zero different places. Like if V1 has the zero voltage set one place, and V2 has the zero voltage set somewhere else, V1 plus V2 is not necessarily going to have the zero voltage at either one of those places. It could be something entirely different and wonky. On the other hand, if these were both voltage functions for a finite collection of charge, and we'd set the zero to be zero the voltage at infinity, then when you add these together, the zero of the voltage is still at infinity. That's true. But I was originally going to write the theorem down with the assumption that the voltages, the zero voltage had to be the same set, but that's an unnecessary restriction on the theorem if you think about it. I mean, the calculus works. Now, how do you put this theorem into practice? Well, you could take all of the examples that you've done and you can mix and match them, right? Like take the uniformly charged sphere and surround it by a spherical shell charge. I can just straight up write down the voltage from example 6 plus the voltage from example 7. There's the voltage for this composite example, because we can just put together what we've already did to make a bigger example, simply like that. Now, so more broadly speaking, this superposition extends to, through integration, to continuous distributions of charge. We can just straight up calculate the integral of the Coulomb potential for an infinitesimal charge dq over the appropriate space. But here dq is either to be understood as like rho d tau or sigma dA or lambda ds, depending on whether we're thinking about a volume, a surface, or a linear charge, like I write down here. So, great. Now, here is a horrible example that you don't want me to write out on the board, but we should look at together. All right. When we get back to basic physical derivations, I will then put this away and write things on the board like a human. Okay? But for the moment, trust me, you don't want me to try to recreate this calculation here on the basis of my minimal brain power. What?
I see a sequence, I believe.
Yeah, this one's nasty. But it's a relatively simple problem. I've got a finite line charge here, just a line segment of charge, Q, distributed from the origin over here to L00. My question then is, what's the voltage? Right? So to do that, I simply have to integrate dV over the line segment, you see, and dV is just this. That's innocent enough. Right? The dq, it's just q over L dx prime. What's the harm in that? And so, yeah, so the q pulls out, the L pulls out, you get your 4 pi epsilon naught. I'm starting to really feel like I need to start using the notation k at some point close to now. Like, how many times I've written 1 over 4 pi epsilon naught, I could have written k. Remember k? Just remember k. What was it? 9 point something times 10 to the something or other. You know what I'm talking about? In the Physics 232 course, the k. But it gives me joy to write the epsilon naught, so I keep doing it. Certain nostalgia for me, for my youth, I guess. But anyway, so, all right. That's we had to do that integral to calculate the voltage to this line segment. Now that's a little bit unpleasant because it's a square root of a square, but if you look at it, you're like, oh wait, that's a trig substitution. It's actually not that bad, sort of. And so, yeah, it's a trig substitution, but it's a little bit ugly. I threw these absolute values on here because I don't want to think about it. So that's definitely positive, right? But probably you should think more about that if you want to be fussy about this example. Anyway, I got this, which, then if you drew this little reference triangle for the substitution, it leads me to this monstrosity here. But you notice something happens. Gone. They cancel, which is kind of cool. It's not going to get much nicer. There you go. That's the voltage for a finite line segment from the origin to L0, 0. And that is why this is not an example in Physics 232, except the year I assigned it as homework. I did that. It's been a while, though. They complained for some reason. I don't know why. All right, so then this example, we have the uniformly charged spherical shell of radius r with density sigma. So Q is 4 pi r squared sigma. This is example 2.8 in Griffiths. This is the kind of, this calculation he does more than one time. So if you try to understand it once, then you'll understand his later derivation, which also uses this, I noticed. But basically, his trick is to say, okay, so we're trying to really find what happens at an arbitrary point far away from the sphere. We might as well put the point on the z-axis where our formulas work nicest. This is a total physicist move, right? Mathematicians would be like, no, it has to be an arbitrary point. We must suffer. Physicists are like, I will put the point where the formulas are nicest and assume half of the problem. Boop, there. And so doing, you've got this triangle, and you can do the law of cosines, which gives you this, and some relatively innocuous calculation later. Well, that's the thing. It's kind of cool what happens. You end up with, when you evaluate from 0 to pi, you get this or that, which are respectively this or that, but that's the absolute value of z plus r, and that's the absolute value of z minus r. So depending on whether z is less than or greater than r, the absolute value will flip or flop, And so what happens here then is you either get, this is pretty cool. This calculation is pretty cool. But this is not the way to do it. The way to do it is the line integral I showed you 5 minutes ago. Because this is the uniformly charged spherical shell. We just did the line integral from infinity into the shell to derive the same result with much less effort, right? But this is how to calculate that same result by doing the Coulomb integral, all right? And so when you do, the z's, they be canceling. So inside, you get this constant, you get the constant voltage, of course, because the electric field's 0 inside. And outside, you get the Coulomb potential, but here we're doing it to z. So that's why the formula is in z rather than r, because he's let z be the arbitrary distance away from the center of the spherical charge. That's a pretty beautiful calculation, I think. So that brings us to this, which is the point at which I should put this away. So, at least for now, I reserve the right to bring it back if I grow discontent with this, with the density of my truth. Let's see here. All right, so this picture contains the story of the course so far. It's a beautiful picture, really one of the nicer things that Griffiths has done in this book for sure. I don't know if this is original. I don't know the history of all, junior level physics books. I'm not that versed in it, I know there are harder books that were around before Griffiths. Griffiths is dumbed down from what existed before it. I'm pretty sure. But you're probably like, I think it's plenty hard, right? But there's three worlds, and these worlds are connected. You've got the world of the electric field, the voltage, or the potential, right? Now, to get from a given potential to voltage, we can calculate the Coulomb integral, right? 1 over 4 pi epsilon naught. We integrate rho over script r d tau, right? I guess, I mean, to be fair, I should probably put a prime here. We usually do, right? We do the integral. We integrate over the source region of the density, and that gives us the voltage, right? If you want to go the other way, what do? Remember that the Laplacian of the voltage is equal to minus density divided by epsilon naught. So to go the other way, if you just calculate the divergence of the gradient of the voltage, you've got the density after you suitably multiply by epsilon naught and put a minus on it. To get from voltage to electric field, well, that's easy enough. What's that? Yeah, so to get from voltage to electric field, we go minus the gradient. E equals to minus the gradient of the voltage. And how do we go the other way? To get from the electric field to the voltage, our formula V of R, right? Minus the integral from, let's say, infinity to E dot dl, right? To R. That's our how to get from the electric field to back to voltage. That's how that goes, right? And what else can we say? How do you get from the electric field to density? Yeah, Gauss's law, right? The divergence of the electric field is rho over epsilon naught. And how do we get from the electric field, from the density back to the electric field? We have this lovely formula. Remember this one? E is 1 over 4 pi epsilon naught z integral of rho of r prime over z script r hat divided by the script r squared d tau prime. And I'm just writing them like they're volume charges, but of course this picture can be adapted for line charges or surface charges, and it doesn't have to be that the origin's at infinity, but that's just the nicest thing if we can get away with it, all right, for the sake of specificity. So which comes first? Which is physically primary? The electric, the potential, the density? What do you think?
The electric?
Density.
I think density. I think density is what's basic, because we pick out where the charge is, and from that we can extrapolate, what the electric field is, what the voltage is. But truthfully, we could start anywhere here, right? You give me any one of these, we can get the others, right? Not uniquely so, but yeah.
I'm confused how we don't physically fundamentally start the electric field, since it's the fundamental particles that have the field lines.
The fundamental particles have the field lines.
Yes, I have charge.
I mean, the fundamental particles have charge, and because they have charge, they have field lines, yeah. So, but I mean, chicken, egg, these things are all wrapped together is kind of the larger point, right? I mean, you can make more of a case that the voltage is the potential is more of a mathematical construct, right? Because the zero for the voltage is by no means unique. I mean, we're setting it to be infinity here, but that's just a convenience, right? Because the gradient, listen, mathematically speaking, if you have the gradient of V1 is equal to the gradient of V2 on some connected region, what does that mean? That just means that V1 minus V2 is equal to what? Not zero, but a constant. Now, when we're outside the context of electrostatics, when we start talking about dynamics later in the course, this gets a little bit more subtle than that, but still the voltage is not unique. All right? There's always this freedom, which we ultimately learn as a gauge freedom. So what are the key features of electrostatics? Well, let's review. The key features really is that if we integrate E dot dA, right, we get the charge enclosed over epsilon naught. And we also have that the integral of E dot dl along a loop is what? Zero, right. Not a trick question. So, what does that tell us about the relation between like surface charge density? And so what we like to look at now is the question of boundary conditions. What can we cipher from these relations about how the electric field has to behave above and below a surface, right? That's the question I want to ask and answer here. Oh man, what was that? Oh, there's a piece of tape in here. Ew. It's very gummy, like ancient electrical tape that's coming undone. Why is that even in there? I have no idea. All right, so, oh, don't breathe that. I can tell you from personal experience, the board cleaning stuff, it is not good for your eyes, your nose, or your mouth. I've experienced all three. I've not really gotten into my ears yet, though.
It's probably good for you.
First time, but it's probably good for my ears. All right, let's get nuts. No. All right, so so think about this. We've got a surface with charge density sigma. What's the deal with the electric field above and below that surface? So let us suppose that this is the above, right? So my question is, if we think about a little, we can think about a little, like, I think Griffiths tends to call it a pillbox or something, I don't know. But if it's got cross-section A, right, we can think about the electric field above and the electric field below, right, taking up as the positive. And if we do that, the flux through this little, region is what? Well, it's E above times A minus E below times A. See, because that, the outward pointing normal to the Gaussian pillbox looks like this up here, right? And then down here, you got that, right? So we have the electric field above minus the electric, and I really should talk about the perpendicular field, right? Sorry, I'll get it eventually. And that's equal to what? Q enclosed over epsilon naught, right? But in this context, that's exactly sigma A over epsilon naught. Hence, we find that E perpendicular above minus E perpendicular below must be equal to sigma over epsilon naught. An important example of this is with conductors, right? Do you guys remember the discussion of conductors in 232? How that goes? What's the deal with a conductor? Like, yeah, if this is a conductor, right? We have, among other things, that the electric field is zero inside, right? The electric field has to be zero inside a conductor in the electrostatic case because conductor by definition has free charge which can move around an unlimited supply because we talk about perfect conductors. And as such, if the electric field was non-zero, the charge would be moving and we would be outside the electrostatic context. So voila, the electric field must be zero inside the conductor. And as such, this says what? This says that the E perpendicular field above is just straight up equal to sigma over epsilon naught. in the context of a conductor. Because E below is what? For a conductor, E below is 0. See, so this boundary condition simplifies a bit for a conductor.
So here the top surface of the conductor is coated with a shell charge?
Yeah, exactly. Yeah, well, it has to be on the outside of the surface of the conductor. There can't be charge in the electrostatic in the interior of a conductor. And I'm sorry, I didn't mean for this to be the edge. Like, this is just it's a picture. This thing goes on and on and on and on. I can't draw it. It goes on and on and on. I don't mean this to be like a loaf of charge. I mean a loaf of conductor. I mean, another picture of this would be, here's the charge, and the conductor is like all down here. Right, so my electric field perpendicular above must be sigma over epsilon. All right, so, but the other thing we can do in the same context, right, is we can think about like a loop, right? Yeah, and we can let the loop go like this and like that, and we can talk about, this length being L, let's say. And so we'd have like L times E above minus L times E below. All right. Again, I'm thinking about, a surface with charge density. I'm imagining it a little loop. All right. And I want to think about my loop is not little enough at the moment because I'm imagining. So over here, I really wanted to imagine that this height is going to 0. And likewise here, this h, I want to let go to 0. Maybe it's helpful for me to redraw this picture in a two-dimensional context. Here's my sigma. My loop looks like this. All right? So you're going this way, that way. And so the integral of E dot dl around my loop, right, is just equal to this. The reason being, I'm thinking about in a limiting sense, as h goes to 0. As h goes to 0, the ends of the loop just nothing, and you're just left with the line integral just becomes the value of E above, and here's E below. And I guess with my current picture, E above should probably have a minus and a plus. I don't know, whatever, guys,
Can these be the parallel components?
I was getting there. So and you notice that I can draw that, but yeah, very good question. So I drew it in this way, but this picture equally goes for any choice of parallel direction to the surface. I could put this loop pointing any different which way. So let's just say parallel, like Shane said, because it's not which parallel direction. Well, all possible parallel directions to the plane this holds for, and this is equal to 0, right? We take the limit as h goes to 0, so we're definitely not getting any contribution from the perpendicular piece, right? Yep.
In order to ensure that it's every direction, do we also need to have that the length goes to 0 of the loop?
No, I can take I can, as long as it's big enough to fit inside the surface. If I'm looking top down at the surface, right? My loop could look like this. Here's a bunch of different ones. I could just like this or like that, or any different. Here's the above, here's the below. Think about, think about one inside, yowzers. The board, one outside. Same thing, like outside, inside. Imagine one of these on one side, one of these other, and like the loops like that. I can go like this, I can go like that. As long as the loop isn't so long as to extend past the surface, I can construct I can make the length as long as I need to. Right? I can do this for arbitrary length loops. Yeah? I mean, I could let the length of the loop go to 0, but I think I don't want to. Because the larger point is the length is finite. I factor it out. What does this show me? This shows me that E parallel above is equal to E parallel below. Put this all together, what's this say? This says that the electric field above minus the electric field below is equal to, apparently, sigma over epsilon naught n hat. See, because you can build the electric field from the perpendicular part and the parallel part. Parallel parts match. Perpendicular parts have to differ by the surface charge density divided by epsilon naught. So, there it is. Yeah.
Even though you do have a infinitesimal length on those perpendicular parts, you're passing through a section of infinite charge density. So shouldn't that have some sort of direct delta integral that wouldn't really go down with that distance?
But this is a two-dimensional distribution, and we're doing a one-dimensional. I don't know. But no one cares about that for some reason. But that's a good question. Why doesn't the divergence in the sigma matter there? I think the answer is because the charge is smeared out over a surface and not along a line. I think this would be totally bogus if instead of like, if the sigma wasn't smeared out over, if it wasn't a planar distribution, if it was a linear distribution and one of the lines of my loop went across, like I don't think, to be more specific, if you have this as your line charge, right? I think you would be totally right to be very skeptical of an argument that involved a loop like this, because that is a linear divergence in the sense of it's a linear charge density. And if you have a line, but this is an area density, and so I think it's okay for a line to go across it and not suffer that problem. Likewise with the Gaussian pillbox, the edges that are cutting through it are not, they don't cut through it in a planar sense. They only cut through it in like a, you know what I'm saying? The thing you're worried about, there's just that line, the line in the back, that line, right? They're not planar charges that are being intersected. They're, man, how to make this rigorous? That's a very good question, Sam. I don't know how to deal with that. Nevertheless, this is very helpful. Like this is what the deal is. The boundary condition for the electric field above and below like that. Now, for a conductor, what's the parallel component near the surface of a conductor? What's the deal there? If there was a parallel component along the edge of a conductor, what would happen to the charge inside the duct, right on the edge of the conductor? It would be doing what? It'd be moving, right? So we can't have a parallel component on the edge of a conductor. Otherwise, in the electrostatic case, it wouldn't be static. We'd have moving charge. So in a nutshell, if you have a conductor, it has to look something like, you know, this. There can be hole inside. There could be like a positive charge in here, Q. And of course you can have, that'll induce a negative surface charge in here, right? But then there, you know, if the net of the conductor is neutral, right? If the sum of the charge on the conductor is 0, then you have, you know, positive charge induced out here, right? And how much positive charge? Q. Why is that? So if and I you know, this is where shading really, not having shading on a whiteboard really is such a sad thing. But I'm trying to mean this is a hole, and this is like a solid conductor, okay, with a hole in it. So the point is, if you take a Gaussian surface here, right? What has to be the case? You have to have the flux through that is what? It has to be 0. Because the electric field inside the conductor has to be 0. Which then forces the induced charge on the interior hole to match the point charge that I put inside the hole. So there has to be a charge of minus Q induced on the inside surface. And then if I tell you that the conductor is overall uncharged, that forces us to put a charge of Q on the outside surface. Which leads to the kind of weird thing that somehow the outside world knows that there's a charge in here, even though it's shielded in that sense. It's funny how that works, but it's how it works. All right, so those are the boundary conditions. Now, next up, we talk about like work and conductors. And if you guys would just suffer me like 5 minutes of projection, I think that would, well, I guess I'll stop here. I kind of wanted to get a day ahead because I think it's going to take us longer to get through chapter 3 than I have put down on the schedule, so I was kind of itching to get there. I don't really, like the next part is on work and energy and electrostatics. And I don't really have much to add relative to like the previous course. Like you remember we worked the problems where how much energy does it take to put 3 charges together? How much energy does it take to put 4 charges together? So he kind of goes back through that and he extends the discussion to n charges, right? And I'll just be like 2 minutes, guys. So you'll forgive me, I hope. Hey, I just cut your homework in half. I should have some leniency right now. That's right. I mean, if I was smarter, I wouldn't do this because then I wouldn't have to prepare a lecture for Wednesday. I could be lazy and use the stuff I'd already done. But, all right, so to calculate the work done, the question is like, how much work does it take to move a charge for a given configuration of charge, which produces electric field E, if we move Q from P1 to P2 using minimal effort, then if you think about it, we have the pushing force plus the electric force is going to be 0, right? If we just move it at constant velocity, like just the minimum amount to nudge it along is the idea. And so if you look at that, then that means the pushing force is minus the electric force, but the electric force is QE, minus QE. And so the work done is this, which is that, but you recognize once you put the minus in there, that's the potential difference from P1 to P2, which is pretty awesome. So that's why work is equal to the charge times the difference in potential. It's just the natural consequence of this circle of ideas. And by the way, I can be more system. If I do it relative to the I mean, there's something there. Why is this that? Because if we go to the origin, so like I start out from P1 to P2, I go P1 to the origin, and then from the origin to P2. So I do this path and that path as opposed to the green path, which gives me this is equal to that plus that, which is then establishing that this integral is in fact V of P2 minus V of P1, like I claimed. Nothing deep here. It's just, yeah. So the difference in potential is equal to the work done divided by the charge to move that charge from P1 to P2, which of course gives us the well-known statement that potential is potential energy per unit charge, as you guys remember, right? And so if you look at the assembly of how much energy it takes to bring in charges from infinity to put together a charge distribution, and you work it out, you get this formula. And then what he does is he divides by 2. So instead of I greater than I, j greater than I, he gives just j not equal to I, like this, where, usual distance between the charges. And this is the potential at r sub I is this. And so lo and behold, the work that it's required to assemble n charges at those positions, r1 through r sub I, is just given by this. which it turns out to be equal to like 1/2 the sum of the voltages needed for everything but the ith charge to be there. And then if we simply take the limit as n goes to infinity, this becomes an integration, and we find that the work needed to assemble the charge distribution is simply 1/2 rho times v d tau integrated. And this is pretty neat. Really, the takeaway message from this part we're getting to, this is just the backstory for where that summation came from. Like here's, first charge is free, second charge costs you that much work, the third charge, you got to do this much work to bring in the third one, to bring 3 into play. To bring 4 into play, it costs you this much, right? And you remember, maybe you remember these problems. Yeah, okay, great. Anyway, so that's physics 232. I don't think we need to do that in here. So, but this is here. So the work done to create the charge distribution rho is given by the integral over all space of 1/2 rho times the voltage d tau. But remember that by if we suppose that the charge is within the volume V, right? Then we can this is Gauss's law, right? Rho is the divergence of the electric field, but then integrating by parts here, we can trade out, because notice that there's a voltage here. So by integrating by parts, we have that. And this, though, is actually e squared, because minus the gradient is e dot e is e squared. So you have the integral of the magnitude of the electric field squared over the volume plus this term over here, voltage times the electric field dot dA. And so if we're in the situation where the voltage goes to 0 at infinity, right? As we expand the volume out to infinity, this piece goes away and we're just left with the e squared, right? So in short, supposing that v of infinity is 0, we have that the energy that it takes to assemble it, the energy basically stored in an electric field is simply given by epsilon naught over 2 integral of e squared d tau. And this leads us to the statement that the energy density in the electric field is actually like e squared times epsilon naught over 2. This is the energy stored in the electric field. It works like that. So like here, this example right here, what I've done is I've calculated the work to assemble the sphere. This is the spherical shell charge yet again. And here is just calculating the work done in terms of just calculating over the volume being the sphere to radius r. So the volume term is 0 because the electric field's 0 inside there, but the density is 0 inside there rather. And anyway, so for the spherical charge, that previous formula simplifies to just the boundary term, which integrates like so. If you're outside, if you put your volume outside, like outside the sphere, you end up with just the volume integral because the voltage goes to 0. The other term goes to 0 for large R. And so you're just left with this. But as you can see, I don't know, Griffiths has this sort of, so here's just a quick review of how conductors go. E equals 0 inside a conductor. The density is 0 and net charge has to reside on the surface. The conductor is an equipotential, right? That's because the E is 0, which means the gradient of V is 0, which means V is constant. And the electric field has to be perpendicular to points near the boundary of conductor. So this is all physics 232 stuff really. Here's a happy, don't ask me to draw the electric field in here. I don't have sufficient artistic ability. But these are supposed to be electric field lines. There's more of them where the charges bunch up on corners and they are more spaced out other places, right? I meant to shade this. This is supposed to be a solid conductor. I've got no excuse. I can shade on paper. See, I did it there. And then this is, okay, we're going to come back to this like next lecture, hopefully. Well, maybe not next lecture, but soon. If you have the voltage, you can figure out the surface charge density. So here's a problem we're going to solve in chapter 3. Imagine you have an infinite conducting plane, all right? You put a charge above it. What happens? Positive charge. You're going to induce negative charge on the plane, right? What charge do you induce? Yeah, but how much where? How much charge do you induce on the plane? You think the same charge, but over the whole plane. But how is it distributed? See, we don't know how to solve that problem right now, but after chapter 3, we will own that problem. That's the most basic example of something called the method of images. So hopefully we'll cover that. I might not get to its next class, but we're going to build the machine to justify that. And it will open up a whole new world of examples that you would have trouble doing with Physics 232 methods. So anyway, sorry I've kind of hurried through the end of chapter 2. I hope you'll forgive me. I haven't even shown my capacitor slide, but rest assured there's a slide on capacitors next, so you guys can look at that. But anyway, I'll shut up. Thanks, guys.